Alright, so we're recording here lesson 9, a preview video for lesson 9. And what I have recommended before, and I continue to recommend, is that with every lesson you should take the lesson plan and go through and look at the lesson objectives and really focus on those. And there's definitely going to be some nitpicky details in each lesson. Most lessons will have some details, but it's the big objectives that we're concerned about. So the first objective is to differentiate between cis-trans isomers, okay? We have to get used to it. Cis-trans isomers. All right, the next objective is to identify asymmetric centers. What does that mean? We'll get into it. And the third one is we've got to be able to draw and name enantiomers. All right. So the first thing is I want to be able to differentiate between cis-trans isomers. And what I've done here is built a couple models, and I don't have my small model set with me. This is going to have to be good enough. But what I've got here is, suppose I've got a double bond. This is an alkene. And suppose that every black is just a carbon-carbon bond. And so this would be, 1, 2, 3, 4 carbons. This would be a butene. And the double bond is in the middle, so it would be 2 butene. But you see I've got, something here and something here, a substituent here and there. By the way, notice please that this is trigonoplanar, okay? And this is a great model for alkenes because this stick that I'm holding right now, actually pause the video and tell me what is the stick that I'm holding. The ones that my fingers are touching, what is that? Okay, so you had a chance to look at that. That, it turns out, is an unhybridized p orbital. Alright, and in every sp2 hybridized carbon, you're going to have an sp2 hybridized orbital, an sp2 hybridized orbital, and sp2 hybridized orbital, which overlaps with something else here to make a molecular orbital, which we call a bond. But it's the unhybridized p orbitals that make the side-to-side overlap of a pi bond, which I'm going to take and use like a rubber band right here, okay? I don't have a rubber band for both the top and the bottom, but remember that a pi bond results from side-to-side overlap of these two unhybridized orbitals. So there will be a region of electron density up here and one down here, okay? And so a double bond actually kind of looks like a triple bond, remember? You might want to look that up in the book if that doesn't sound familiar. A double bond has got a pi bond, which has got an upper lobe and a lower lobe, where my fingers would be, okay? And then a sigma bond, which is end-to-end overlap, which is right there, okay? So this is a super model. It's a great model for sp2 hybridized carbons. So what I've got here then is a double bond here, okay? I'm only showing the sigma. The pi is implied by these sticks right here. That said, we know since there's a double bond there, it does not have free rotation about that bond. It does not, because these two electron densities are holding it in place. So that said, this molecule is different than this molecule, right? Because it would require to break, we would have to break this pi bond, turn it over, and reform that pi bond to make this, okay? So this has are two different things, okay? One of these is cis and one is trans, and that's this word here, or that's these two, I guess, prefixes that we're going to have to be familiar with, cis and trans isomers. Cis means that they're on the same side, and trans means that they're across from each other, which is what you might expect. Okay, cis and trans isomers. Now, what I do, let me go just a little bit further before we move on. What I do when I'm trying to draw that, when I'm trying to identify, suppose you've got something that looks like this, CH3, CH, CH3, CH2, CH, CH3. Oops, let me get rid of that H right there and say that this is CH and CH3. Okay? Here, let's draw this out and see if this exhibits cis-trans isomerism. 1, 2, that's going to be a branch, so it's carbon 1, carbon 2, there's a branch, there's 3, 4, there's another branch, 5, and 6, okay? 1, 2, 3, 4, 5, 6, alright, and carbon 1, I've got 3 hydrogens. Carbon 2, I've got a hydrogen and a methyl group, okay? And that's carbon, this is carbon 1, 2, 3. I'm going to call that carbon X, there's carbon X. 4, which is here. 4 looks like 4's got a methyl group coming off of it also. I'll call that carbon Y. Alright, and then 5, and then 6. It looks like 4 only doesn't have any hydrogens coming off of it. It's just that methyl group right there. And this carbon only has 1 hydrogen coming off of it. Carbon 5 does, and a methyl group. There's carbon 6, right? So it looks like that must be a double bond. Now the question is, does this exhibit cis-trans isomerism? So what I'm going to do, of course, a lot of times we'll get it from that, like that with Bruce. With me, I usually go ahead and draw them out like that for you on the quizzes and exams. So either way, we've got to figure out if this, what I'm going to do when I'm doing this, I'm going to isolate the double bond that I'm looking for. I'm focusing on that, and I'm taking all the things that are on the double bond. There's kidney, there's square, there's circle, and there's diamond. Making up those shapes, by the way, okay? But do you see how I've isolated the double bond by doing this? I've got my eyes really focused on that double bond right there, and I'm going to ask myself, if I switch triangle and circle, will I have the same thing, or will it be different? That's what I mean. If I switch them, will it be the same thing, or will it be different? If it's the same thing, is it the same after switch? Yes, it's the same. Then it does not have cis-trans isomerism. Okay? If it's not the same thing after I switch it, then yes, it has cis-trans isomers. Okay? So there's an example, and to keep this video short, I'm not going to give you another example. You may want to go back and look at this again. Actually, you know what? I'll give you one to go on a quiz, okay? Suppose, you tell me now. I'm not saying this will be on your quiz. I'm only saying that you tell me, does that exhibit cis-trans isomerism? And I'm going to leave objective number 1 off with that. Okay, let's go on to the next objective. The next objective is to identify asymmetric centers. Okay? Let me pause this for just a second here.